Hello everyone, and welcome back to the garage. This is part 2 of the restoration series on this 1978 Gottlieb Close Encounters of the Third Kind pinball machine. And in this video, we're going to be finishing up the cleaning process. We'll get the underside of the playfield and the coin door all cleaned up. We'll start doing some electrical testing of components both in the playfield and up in the back box. We'll take the boards out and see how they look. And if everything checks out during my testing, we will plug this machine in and power it up for the first time in 40 years. So let's get started. So one thing you can do on these Gottlieb System 1s to get better access to the bottom part of the cabinet is you can actually remove this entire wood panel from the system. It's just held in with these two massive flathead screws here. So if you undo these, I'm gonna have to voice over the rest of this clip because there was some background noise outside that was too distracting. So once you get those screws removed, you have to remove this connector, this screw for the wire harness, and then there's another one deep in the playfield on that same harness. And once you do that, you can go ahead and just lift open the panel like this. And at this point, it's not removable. You would have to take out some more connectors and wire harnesses, but it gives you enough access to the underneath of the cabinet below the panel so you can clean it up. And in this machine, it actually wasn't that bad, which was nice to see. All right, so this is what the coin door looks like after its first pass of cleaning. As you can see, it's not in the best condition. We have some oxidation and rust spots around the lower 3/4 of the door, but I was able to get a lot of dirt off of this Gottlieb sticker here with some alcohol, and it looks a lot better now. The alcohol did not cause this paint smearing. It was like that when I got the machine, so obviously someone tried to clean that sticker with something else and caused the paint to smear. I do still have to clean around the start button. As you can see, it's quite dirty in there. I'm going to take out the button. It's just held in with a couple screws right here, and then this is the switch for it. So I'll take that out and clean in there. I put 2 warm white LEDs in the sockets in the coin door, and I also cleaned out the coin return area. I took out the little bracket that the coins fall into, and it was very dirty in there. I had to use WD-40 to get all of the ground in dirt out because none of my other cleaners would do it. So that looks much better now. The inside of the coin door isn't actually that bad, and I was planning on taking out the entire internals of the coin door like I did on the Phoenix, and it looks like you can do that by taking out these 4 little metal clips. I tried doing that, but it wouldn't budge, so I think I'm just going to leave that alone. And I think that's okay to do because if I look inside here, if I actually look in, like in here and back in there, it's not that bad. So I'm just gonna leave the coin door on, but I did go ahead and clean all of the other coin door pieces. That is what these look like now. I took out the price signs and I cleaned the little inserts. So now the front of this looks quite a bit better. I got the sticker residue off the middle part of the coin door here. You can kind of still see it, but I don't think there's anything I can do about that because now it's nice and smooth. So I think this little residual part has to stay there. But the rest of it looks great, as you can see. I cleaned up the coin return pieces. They were extremely dirty, and I had to use WD-40 on those as well to get all the ground-in dirt and grease off. These are the two coin mechanisms, and they were actually okay. But I did have to make an adjustment to both of these coin mechanisms because if you look on the back, they're Canadian coin mechanisms, but I think they're designed to accept US quarters because they are identical to a US quarter mechanism, which is this one here, except for a couple things. The Canadian mechanisms don't have this magnet in here, and all that does is just slow the coin down when it goes through the mechanism. And it also prevents foreign coins from going through it. Like, so if I put in a Canadian coin into this mechanism, the magnet would stick to it and the mechanism wouldn't allow it to go all the way through. So you'd have to use the coin reject to get that out. So the Canadian mechanisms don't have that magnet, as you can see, but they do have a couple adjustments that the US mechanisms don't have. There's a little adjustment right here for the size of the coin that goes up and down a little bit, and they don't have this adjustment for the diameter of the coin going into the actual mechanism. As you can see, the US mechanism doesn't have this adjustment, nor does it have the adjustment here. So those are the only differences as far as I can tell. But the problem with the Canadian mechanisms is since there's no magnet here, whenever you try to put a US quarter through it, it goes straight to the coin reject every time. And I don't think it was supposed to do that because on my Williams Phoenix, I got it from the same place as I got this machine. It also has Canadian quarter mechanisms in it. And there was a sticker on the front. It was extremely faded, so I removed it. And it says, it basically said, don't use Canadian coins. So they were designed to accept US quarters, but for whatever reason, these specific mechanisms, whenever you put a quarter through it, it goes straight to the coin return. So what I ended up doing is I put a little tiny piece of a magnet in there, and it doesn't have to be a magnet, it just has to be something that you can stick inside the coin mechanism. See if I can open this with one hand since we're not on the tripod at the moment. So as you can see, I stuck a little piece of a magnet right there. And so now, regardless of what position the coin mechanism is in, if it's like this or if it's mounted like that, a US quarter will always go to the right place, which is right here. And when it comes out of there, it will trip the switch on the coin door for the machine so that it will rack up a credit. And so it will always go through that slot if it's a US quarter. And if it's something else, it will go straight to the coin reject. So these coin mechanisms, I basically made it so that when you put in a quarter, it will always accept it. So that's a little thing that I did to both of these coin mechanisms. So now they work correctly. So now I just need to put the pieces back on the coin door and then that will be done. And here's the coin door after it is all cleaned up and put back together. As you can see, it looks quite a bit better than how it started. One thing I did have to do when putting this together is I had to fix the coin reject mechanism because for whatever reason, when you push the button on the front, it would not push down the coin mechanisms to the point where it would make them separate like that. And so the issue was this little piece here that the metal rod pushes against was bent too far back. So all I had to do is just loosen the screw a tiny bit, and now that piece is in the correct position. So now when you hit the button, it'll actually push down the coin mechanism rejects far enough so that the mechanisms will move and reject the coin. So that works now. I also went ahead and lubricated the hinge because it was squeaking like crazy. Now it's nice and silent, and it is noticeably smoother when moving the door. So that is all nice and clean. And so now we are ready to start doing electrical testing on this machine. We'll go ahead and test all of the components necessary to this thing being able to power itself up correctly. And then after we're done doing that, and if everything looks okay, we'll go ahead and plug this machine in and see what it does. So in terms of the bottom panel down here, the only thing that I want to test specifically on it are the two bridge rectifiers right here, just to see if they are working properly. And we can look at the schematic, which I have open right here, to see how they're wired. So these are the two bridge rectifiers right here. And as you can see, we have a red and white wire connecting one of the 5 amp slow blow fuses to one of the pins on the bridge rectifier. And then there's another red wire right here. So if we measure between the red and white wire and this red wire on diode test, we should have a voltage drop one way, but not the other way. And same for the rest of these diodes on here. Each bridge has 4 diodes in it. So we need to do 8 different diode tests. All right, so the bridge rectifier with those 2 wires is this one. So if we put the negative lead on the red and white wire and the positive lead on the red wire, we should have a voltage drop. There we go, voltage drop of 0.78, that looks good. And so if I turn the leads the other way, there should be nothing. Well, we do have something, but that's probably just because it's in circuit. If I were to remove the bridge rectifier, it probably would show nothing, so I'm not concerned about that. We saw a good voltage drop, so that's what I want to see. I want to see that the bridge rectifier is actually working and that it's not open or shorted. And just by doing that test, it's not open or shorted, at least not in that diode. Now if we go between the red and white wire and the black wire, we should have a voltage drop. So that's this wire. Okay, there we go. That diode is fine. Turn it around. Yeah, that's probably just an in-circuit thing because we got a voltage drop. So now we're gonna do the black wire and the black and white wire. So that is going to be this. Okay, looks good. Turn it. And then the last one is the black and white wire and the red wire. Okay, so that bridge rectifier is good. Let's go ahead and test the other one. So in this one, we have to test the orange and black wire and the white wire. These two. Oh, do we have an open bridge? Do we have an open diode on the bridge rectifier? Certainly seems like it. Let's turn the leads around. Maybe not. I turned the leads around and now we have a voltage drop, so maybe I just wasn't making good contact. Orange, black, and the white. That's interesting, because if I put the negative on the orange and black and the positive on the white, we should get a voltage drop, and we don't. But if I put the negative on the white and the positive on the orange and black, we get a voltage drop. So I might have to desolder the bridge rectifiers just to verify that they're actually working. The next one is the black wire and then a blue and red wire. No voltage drop, but if we turn it around, we get a voltage drop. That's interesting that in the reverse direction we get the voltage drop. And then the final one to test is the blue and red wire and the white wire. Okay, no drop. Okay, so that means that they're not open, because if they were open, we wouldn't get a voltage drop in either direction. So the bridge rectifiers, they're not shorted, they're not open, which is good, but I might have to desolder them just to check and see if they're actually working, because tests in circuit are not conclusive. So at some point I'll have to desolder those and see if they're actually working. So we know they're not shorted, they're not open. So we tested those and they seem like they're okay. I imagine they're fine. I assume that take them out of circuit and test them, they'll be just fine. That won't be for later. For now, I want to test the boards in the system and see if everything is working okay, because that is the major thing that I want to check. So let's get started with the first board, and I think we will do the sound board first because it's right there and it'll be the easiest board to test. All right, so here is the tiny little board that is responsible for driving the sounds of this machine. Now, unlike the Williams Phoenix, this machine can only produce tones. It doesn't produce like synthesized sounds like the Phoenix does. It just produces tones of different frequencies. So that's why this board is much smaller than the one in the Phoenix. So really the only things that I need to test on it are these three capacitors, this transistor, I believe this would be the voltage regulator, and then this pot, which I assume controls the volume. So those are the only things that I need to test on this board before plugging it back into the system. So what I'm gonna do is I'm gonna desolder these three capacitors so I can put them through my leakage tester, and we'll see if they still work properly. All right, and there are the three electrolytic capacitors desoldered from the board. And just by the looks of things, it looks like these capacitors have gotten hot, and that's not due to the capacitors themselves. It would be due to the surrounding components getting hot. Like if you take a look right here, you can see this big resistor has a lot of discoloration on the board around it. So obviously this resistor gets hot when the board runs, and so that is why these capacitors have a little bit of a burn mark toward the bottom. So it doesn't look like they've been leaking, because if you look at the actual capacitor leads, there's no oxidation or corrosion on them at all. So that gives me hope that these capacitors are actually still good. So let's go ahead and run them through my leakage tester and see what they test like. Okay, so here's the tester right here. It's a Heathkit IT-28 capacitor checker. And a word of warning, if you have one of these and want to use it, these can be very dangerous if you don't know how to use them. So if you use one of these testers, you're doing so at your own risk. I would recommend reading up on exactly how these things work before using them for the first time. So first, what I want to do is check and see if these capacitors measure the correct capacitance that is marked on the actual cap. So let's do this one first. This is a 470 microfarad 50 volt cap. And so what we want to do is make sure that all the settings on the tester are correct. So it is set to electrolytic capacitor test, and it's in the discharge position. So that means there is no voltage going through the clip leads right now. So what we want to do to test capacitance is hook up the leads to the capacitor in the correct position, because these are polarized capacitors. And so once those are hooked up, we can go ahead and set the scale, because as you can see right here, we have a little pointer that we can rotate. And so we have to set the tester to use the correct scale so we can get to the 470 microfarad mark. And so it looks like it's already set to that scale. It's going to be the innermost scale. And I know it's really hard to see, so I'm going to zoom you in here. So now you should be able to see the readings on the actual tester. So as you can see, I move the pointer out of the way, the innermost scale we can get 200, 300, up to 1,000 microfarads. So what we should see, I'm going to flip the switch from discharge to bridge mode, and the eye tube closes. So what we want to do is adjust the pointer to the position where the eye tube is fully open, and that will show the capacitance of the capacitor. So let's go ahead and turn this, and it should open around the 470 microfarad mark. As you can see, it's starting to open. So we want to adjust this to a point where it is fully open. So that would be about right there. So as you can see, it's a little bit above the 500 microfarad mark, and that is typical for an older capacitor to measure higher than what it's rated for, and that could possibly be due to leakage, because when capacitors leak, they develop internal resistance, and it makes the tester that you're using show a higher capacitance like this when it's actually testing the capacitor. So the capacitance is very close. So let's go ahead and flip this back to discharge. And once the eye tube is open, then it is safe to remove the clip leads if you're done testing. What I want to do now is test for leakage. So what you want to do before testing for leakage is make sure this voltage knob is all the way down at its lowest position. So that would be 3 volts, because when you flip the switch to leakage, whatever this dial is set to, there will be that many volts going through the clip leads, and this dial can go all the way up to 600 volts. So that is why these things can be dangerous. So please read the manual for these testers before going and using one for the first time. So I'm going to go ahead and flip this to leakage mode, and if the capacitor is not leaking, the eye tube should be open after I flip the switch. Okay, that's good. So what we want to do is adjust the voltage dial to the closest setting to what the capacitor is rated for. So this capacitor is rated for 50 volts, and we do have a 50 volt setting for the voltage knob. And when you're adjusting this knob, it's important to not go over the rating of the capacitor. So because we have a 50 volt setting on the tester, we're going to slowly increase this up to 50 volts. And if at any moment the eye tube stays closed, the capacitor is leaking. So let's see what we got with this one. So that's 6 volts, 10 volts, 15 volts. I saw the eye tube move just a little bit. 25 volts, the eye tube is opening, so that means the capacitor is not leaking, and 50 volts. So if this stays closed, then the capacitor is leaking, but I can see that it is starting to open, and right there, the eye tube is fully open. And so that means this capacitor is not leaking at 50 volts, so it is perfectly fine to use. And so when you're done testing a capacitor for leakage on this tester, the proper way to be safe with these is to turn the voltage down all the way back to 3 volts, then flip the switch back to discharge. You can see how the eye tube closed when I did that, and it's staying closed. That means the capacitor still has charge in it. And so once the eye tube is open again, then the capacitor is discharged, and now it's safe to remove the clip leads from the capacitor. So the first capacitor that we tested is just fine. So let's go ahead and test the other two. All right, so this next one is a 220 microfarad 25 volt cap. So I'm gonna go ahead and hook this up. So first we'll do capacitance. So let's flip this to the bridge mode. And the eye tube should be fully open around the 220 microfarad mark. Right there. So looks like we're about 250 microfarad according to the pointer. So this capacitor is measuring very close to its proper capacitance. So that's nice to see. So let's go ahead and flip this back to discharge. And now we'll flip to leakage. So this capacitor is rated for 25 volts. So let's adjust this up to 25 volts. So we're at 3 volts and the capacitor is not leaking. 6 volts, 10 volts, 15 volts, 25 volts. That capacitor is perfectly fine. Not leaking, and it measures very close to its proper capacitance. So this capacitor is good to use. All right, and the last one is a 22 microfarad 35 volt cap. Okay, so for this one, when we flip to the bridge position, the 22 microfarad mark is right there at that point. As you can see, the scale gets a lot wider down toward the bottom. So let's flip this to bridge, and the eye tube should open when I flip the pointer down to around the 22 microfarad mark. So it is opening, and it is fully open right there. So it is testing as 27 microfarads, so very close. That is fine. And now I'll flip to leakage. So this capacitor is rated for 35 volts. So I just flipped it. We're at 3 volts and it's not leaking. But the closest setting on the tester we have is 25 volts because after that it goes up to 50. So we're going to test up to 25 volts. So here's 3, 6, 10, 15, 25. That capacitor tests like brand new. It's amazing. So this capacitor is perfect. So all 3 electrolytic capacitors on the soundboard test fine. Okay, so for this next test for the voltage regulator in the pot, the only thing that I want to do is check the resistance on both of these. I want to see if this is open or shorted, and I want to see if this potentiometer actually works. And so for that, the only thing we need to use is a meter that can check resistance. So these meters, how they work is they have a size C battery installed inside them, and that makes the ohms measurement work correctly. So when you flip it to ohms, the needle should go to the infinite resistance or open mark on the meter, which it is doing. And then what should happen is when you touch the two probes, it should go right down to 0. And it gets very close, so I do need to adjust it a little bit. So let's check the voltage regulator. And so all we need to do for that is just see where it's connected. So that's these 3 points right here. And I'm going to put the probes across each of the 3 points and see if they're shorted. If they're shorted, the resistance will go down to 0. Okay, so that's open. And if we flip it, there we get resistance. So that tells me that this regulator is actually working, because one way we have resistance and the other way we do not. So I'm going to do that to each set of pins. So here we have resistance. Let's see if we can get a good connection right there. And we're at the resistance times 1 scale. So that's measuring about 12 ohms on the scale. And if we turn it around, there should be nothing. Well, we actually do have something. And that's probably due to it being in circuit as well. Because when I was testing transistors on my Phoenix pinball machine, it did the exact same thing in circuit. It tested with resistance in both directions, even though the transistor itself is perfectly fine. So I don't think this is a problem. And I'm just going to do these last 2 pins here. So this way we have nothing. The other way there should be resistance, and there is. So it seems like this voltage regulator is working. It's not open or shorted, and it is acting normal for being in circuit. So now the next thing we need to do is test the volume pot. And so to test a potentiometer, you need to hook the negative lead to the center tap of the potentiometer, and then the positive lead to one of the 2 other leads. It might be easier to do it on the top side, actually. Yeah, because I can clip right onto the base of it right there. So then we'll go ahead and we'll just hold the probe on one side of it. Now we should see resistance here, actually. Okay, so holding it up to the leg here, I don't see resistance. But what should happen is when I turn the pot, we should get resistance, and it should change as the pot rotates. And I see absolutely nothing. Could this pot be bad? This pot might be open, because we're getting nothing on that lead. Oh, there it goes. A little bit. Well, that behavior would almost suggest that the pot is very dirty, because you can see I have the pot turned all the way up right now, and if I turn it down, you can see the resistance increases and then it goes open at every other position. Let's test the other lead. Oh, here we get resistance. Okay, so right now it's turned all the way down and it's measuring 12 ohms. So let's turn it up, and the resistance should increase quite a bit, I think. Well, maybe not. That's not normal behavior. The resistance should increase quite a bit. So what I'm going to do is I'm going to go get some lubricant and spray it inside the pot, and we'll see if it fixes itself. And anyone who watches Adrian Black, Adrian's Digital Basement on YouTube, is going to love me for this. We're going to use deoxit. So now what we'll do is we'll take a screwdriver and insert it into the slot on the pot. That rhymes. And we'll just turn this a few times, just up and down, to spread the contact cleaner. And I got a little bit of it on the board, so I went ahead and wiped it off. So now let's test it again. So in the position it's in right now, let me just check. Okay, it's all the way down. So we're going to put the clip lead, the negative lead, on the center tap, and then we'll hook the positive lead up here. So right now we have no resistance. Actually, you know what? I'm going to flip this into a higher resistance setting. Maybe it's just so high that it can't display it. So let's see. Okay, so if I flip it to the resistance times 1000, that shows we have 30,000 ohms. I don't know if that's right, but as you can see, if I let go and then put it back on, that's what it measures as. So, you know what, I'm gonna go get another clip lead so I don't have to hold that on there. When I turn the pot, the resistance should change. So let's see what it does. There we go. You see how I'm turning it, and now it's changing, and it's changing with the movement of the screwdriver. That's normal behavior. So the pot definitely needed some contact cleaner. All right, so with this meter, let's go ahead and check the pot. So go ahead and hook up to the lead on the right. 28 kiloohms, and that's basically what we were seeing on the vacuum tube meter. When I turn this up, the resistance should decrease. Okay, there it goes. So now it's getting lower. That's the nice thing about a modern meter, is that it adjusts the range for you, so you don't have to change the range. So all the way up, we have 22, 21 and a half ohms. So in this position, it's working, because you can see I'm turning it very slowly back down, and the resistance is increasing very slowly. So that is how it should work. So turn this all the way down. Now I'll go ahead and hook it up to the other side. So all the way down on the other side, we have 18 ohms. Let's go ahead and turn it up and see if it increases now. Okay, it is increasing. So I'm turning it very slowly up. As you can see, the resistance is increasing. And so when it's all the way up, I imagine that it will be very similar to the other way. So it'll probably be around 30 k ohms, or about 24 k ohms. That's fine. Okay, so we can see that the potentiometer on the soundboard is working. So it seems like the soundboard is working a-okay. So I'm gonna go ahead and resolder those capacitors, and then we'll take a look at the next board. Well, I went ahead and took out the 3 boards from the back box. So we have the power supply there, the driver board there, and the main CPU board right there. But I discovered a very big problem that is going to prevent me from turning on the machine with this board installed, and that is this battery has leaked more than I expected. The board isn't damaged, but if you take a look on the back side, we have some serious corrosion on some of these bottom connectors here. And so I'm gonna have to use some sandpaper to get that corrosion off so that those can make a good connection again. The traces don't look damaged, so I'm getting to this board at just the right time. And there's a tiny little bit of battery leakage in the area where the battery is, but it's not too bad. So I am going to have to remove this battery. But the other thing I discovered is that the corrosion also affected the connector wires themselves. So this is one of the harnesses that plugs into the bottom of the board here. This connector plugs in right there, and then this other side goes into the driver board. And on the control board side, if you look in there, most, if not all, of the pins in this connector are broken and corroded. So this entire connector, along with the other 2 on the bottom here, need to be completely repinned, because the machine will not be able to work properly with those connections being broken and corroded. The driver board side on this connector looks fine, so this doesn't have any corrosion in it, and the pins are all still there. They're all still bent up. You can see how they're bent a little bit, so that when you insert it into the board, it will make contact on the little contacts on the board here. Well, on the CPU board side, they are no longer bent up because they're broken. There's a few that are still bent up, but 90% of them are no longer functional. So I'm gonna have to repin this connector plus 2 more that are part of the wire harness inside the game. So if I go ahead and open this up, you can see this is what it looks like with all the boards removed, and it's actually pretty clean back here. There's a tiny little bit of dirt on these little metal parts that stick out, so I just vacuumed all that off, and now it looks pretty good back here. So the other 2 connectors that are gonna need repinning are A1J6. You can see this one has a broken connection inside it. It's about to fall out of the connector. That's the worst one. And then A1J7. This one's not terrible, but it will need to be repinned because if I look in there, I do see a couple that are broken, and quite a lot of them in here are corroded, so I'm just going to repin this one as well. The rest of the connectors are fine. They don't have any corrosion and they're not broken, so that's good. So those three connectors I'm going to have to repin before we can plug in the CPU board and test that. But what we can do for now is continue with the testing of the power supply and the driver board, and we can actually go ahead and do the battery on this board as well. So once we test the power supply and the driver board and see that they're working, we can actually plug in the machine and power it on with just the power supply and see if the thing can actually run and give out the correct voltages. So once we get these boards tested, that's what we'll do next. So let's get started with testing some of the boards. All right, so here is the CPU board. Gottlieb calls this the control board. This is the main board that basically handles the operation of everything. And so the only things that I want to do on this board are take out this battery and replace it, test these two electrolytic capacitors here, and clean up the connections on the backside of the board. And one thing that I noticed about this board that I thought was kind of funny is these three dip switch banks are what change the game settings on this machine. And I realized they're actually in sockets. They're not soldered directly into the board, so you can remove these. See, they just come right out. So these are replaceable if for whatever reason your dip switches went bad and you couldn't get them to work with contact cleaner. You can replace the entire switch assembly here. So all three of those are in sockets, so I thought that was kind of funny. Right here we have the game's PROM. It's this tiny little chip here, and each game used a different PROM, so make sure that yours is correct. In the back box, it said that it uses the PROM marked with a letter G, and this chip has the letter G painted onto it, so it's the correct chip for this machine. So let's go ahead and do the first obvious thing to this board, and that is remove this battery. And this battery is actually a nickel metal hydride rechargeable 3.6 volt battery, and you can convert this to use AA's, but you have to install a blocking diode so that it doesn't try to recharge those AA's. But for this machine, we're going to convert it to a clock battery because the terminals that are underneath this battery, I'll show you on the back of the board here. These are the 4 terminals for the battery, and these 2 don't connect to anything. They're just there for support. So what we can do is install the CR2032 with one of the terminals on these unused pins, and then we can install the blocking diode from one of the unused pins to the positive voltage pin. So let's go ahead and get that removed. Oh, it stinks. And now, if those connections are free, the module should just pull out, but I might have to go through them with my iron again. And there we go, it's pulling out. There's the battery out. So now that that's out, we can assess the back of the board, and it looks pretty dang good. Let's take a look at the front and just see how things look. Yeah, we definitely have some leakage. You can see the corrosion on these pads here. So I'll go ahead and clean that up with some IPA and get that looking better. All right, that looks quite a bit better, and I can see around the area where the battery was, there is no trace damage. I mean, there's some corrosion inside some of the traces, but it didn't get to the point where it actually damaged the traces and I have to do repair on those. So that's good. We can just install the CR2032 battery right away. So because I don't have any CR2032 sockets, we're going to use one of these style CR2032s with the legs soldered right to the battery. So what I'm going to do is, as you can see on the silk screen of the board, this terminal is labeled as negative and this terminal is labeled as positive, and so are these 2 terminals here. Well, what we're going to do is we're going to put the negative lead of this new battery into the negative terminal, but we're going to put the positive into one of the unused terminals, because what we're going to do is install the blocking diode from, let's say, this terminal. This is probably the one I'm going to use, and we're going to install the diode between this point and this point, which is the positive terminal, so that it doesn't try to charge this battery, which is non-rechargeable. So we'll go ahead and get that underway. So that is going to be installed just like that. I just have to solder it down on the other side. Okay, I just thought of a really nice way to make this installation look super clean. So what I was going to do was install the diode like this, put it through the positive terminal, and then just have the other end soldered directly to the battery leg here. But what I can actually do is put the terminal that goes to the battery in this other unused terminal, so that when I install it, I can install the diode like this, and look how clean that looks. And then after I solder that in, what I'm going to do is I'm going to run a wire from the unbanded end of the diode terminal to the terminal of the battery on the back of the board here, and it's going to look super clean. And there we go. It is complete. We have a tiny little bodge wire connecting the diode and the battery together. And from the front, it looks factory. Like it looks like that's how it was designed. Battery and the blocking diode. So there we go. Battery has now been replaced. Okay, so the next thing we're going to do is test these two capacitors here. 124, this one might be leaking. 111, that's much closer. I'm going to run these through the leakage tester real quick, and I'll just see what they're like. So I'll give you a close-up of this board. This is the good unused connector. This is one of the bad corroded connectors. And here are the other two. So we have to clean all that off to the point where it'll look like this. All right, so here is the driver board. As you can see, it's a pretty small and simple board. Down here we have the solenoid transistors. That's what all these bigger transistors are down here at the bottom. And then all these little transistors here are for each individual lamp in the game. Gottlieb did not use a lamp matrix in these System 1 games. They did use a matrix for the switches, but not the lamps. So that's why they used a whole bunch of transistors to do the lamps. And if we take a look at the back of the board here, you can see it looks very good. I can tell it has never been reworked before. The contacts on this one look okay. I'll still give them a clean, but they don't have any corrosion on them like on the control board. So for this board, what I did to save time is I already went ahead and checked all of the solenoid and lamp transistors, and every single one of them is good. So that means all of the solenoids and lamps should work when we power the system on for the first time. And I made sure to test the knocker coil transistor, which is this edge one here, and it's fine. So that coil getting burning hot did not fry the transistor. So all the transistors are good. And I even checked these little blocking diodes here, these 4 and these 3. These were added on the later revision of the driver board. It originally did not have these diodes, and I think that is because if one of the transistors were to short, it might backfeed voltage up to the control board and fry stuff. So it's nice to see that this driver board is the version with blocking diodes. So that means the CPU board has more of a chance of working than it would if this thing didn't have blocking diodes. And one thing with the control board as well is I've been reading about troubleshooting and going through Gottlieb System 1 machines, and I was reading about this board, and there were 4 different revisions of this board. There was a 001 version, an 011, an 021, and an 031. And as you can see, this board right here has the 031 at the end of it. So this is the final revision of the Gottlieb System 1 control board. So that is nice. And something I also found on this board was the PROM socket here. I took this chip out of it. It had a whole bunch of rust inside the socket, so I went ahead and used some isopropyl alcohol to clean off the socket, and so it looks much better now. And then I used a little metal file just to sand the little bit of corrosion and oxidation off the legs of this chip here, and I put it back in the socket, so now that should work fine. All right, so now let's take a look at the power supply. The board is mounted to a big metal piece here, and so to actually get that off, what we have to do is desolder the 2 points of this big transistor. If I turn it over, you can see we have a transistor right there, so we have to desolder that and unscrew it, because as you can see, it's screwed into the board right there. So we can remove that, and then we also have to take the nuts off of these 2 transistors here. I assume one of those 3, or maybe all of them, our voltage regulators. And then we also have to remove 2 more screws that screw into the actual board. So once we do all of that, then this board should be able to come free of the metal piece that it's mounted to, and then we can start testing the power supply. All right, I've gone ahead and separated the power supply board from the mounting plate, and it's kind of funny how they chose to mount the transistor on the back of this plate. They have a little piece of plastic here that the transistor legs are set into, so the transistor can't actually go anywhere. And as you can see, it kind of just falls into 2 holes here. So the transistor will stay with this plate. And this transistor is actually the 5-volt regulator, so we'll test that to see if it works. And another thing that you want to make sure you don't lose are these 2 little pieces of plastic. They go underneath the transistors that are mounted here, and those prevent the transistors from shorting to ground when they're being activated. So you want to make sure that when you put this board back in, put these pieces right back where the transistors are supposed to go so they don't short. So these 2 transistors are mounted on the back of the board, and this one's just a regular NPN transistor, but this one's a voltage regulator. So we're going to have to test both of those to see if they're working. So the next thing I want to do is desolder each of the electrolytic capacitors on this board so we can test them and run them through my leakage tester. So I'm going to get started doing that. Okay, I desoldered the capacitors for these 2. All I did was I just clipped off one of the leads so I didn't have to remove them from the board. The rest of them were mounted straight on, so I had to actually remove them. But taking a look at where they were, it looks like we might have a few leaky capacitors because there is some goo under where they were at. And if I take a look at some of these smaller ones, this one might be leaky because it's got a little bit of goo under it, but we'll figure that out when we put them on the leakage tester. So let's go ahead and do that. Okay, first let's check the 2 big ones that are still on the board. So I'm going to go ahead and hook these up. So this first capacitor is a 5,000 microfarad 20-volt capacitor. Now this tester can only measure up to 1,000 microfarad if you're testing capacitance. So we can't test for that, but we can test for leakage. So the closest setting we have on the voltage dial is 15 volts. So we're going to test up to that. So let's flip to leakage. Good at 3 volts. 6, 10, 15. And the eye tube is opening, so at 15 volts, this capacitor is fine. So the other one on the board is a 200 microfarad cap, and it's rated for 150 volts. So let's test this one's capacitance, since we can actually do that on this one. So we'll flip to bridge. So the eye tube should open up around the 200 microfarad mark. About right there. The pointer's pointing at the 300 microfarad mark, so it's possible this one is leaky, but it's not open or shorted, so that's good. So now I'll flip to leakage. 3 volts, it's good. So this one, we can test up to 150 volts, so we're gonna go up to that. So 3 volts, 6 volts, 10 volts, 15 volts. Ooh, we might have a bad one here. It's not touching, but you see what the eye tube's doing? It's not fully open, and it actually looks like it's closing. I'm gonna go up to 25 volts. And look at that. The eye tube is staying closed. We have a leaky capacitor. So this capacitor will need to be replaced. So now we're going to test this other one. This is a Nichicon cap, so I have a little more faith that this one is going to work. You can see it's made by Nichicon, and they usually make good quality capacitors. So the Nichicon is a 1,000 microfarad 35 volt cap. So this being a 1,000 microfarad cap, it is right at the end of this thing's scale in terms of capacitance measurement. So let's go ahead and measure this. And it should open around 1,000. And it opens right above the 1,000 mark. So this cap seems like it is working fine, but we'll know for sure when we flip this to leakage. So 3 volts, it's good. This is rated for 35 volts. So we'll go up to the 25-volt point on the tester because that is the closest setting we can use without it going over the capacitor's rating. So 3 volts good, 6 good, 10, 15, 25. It's closed, but let's see if it opens. And it looks like it is. So this capacitor is good, and I had a feeling it would be. So now we'll test the smaller caps. This is a 470 microfarad at 10 volts. So first we'll test capacitance. That's pretty dang good. That's very close. It's right under the 500 microfarad mark, so the capacitance test is right on. So now we'll test leakage. 3 volts is good. So this is only rated for 10 volts, so we only got a couple settings on the dial that we can go to. So 3 volts good, 6 volts good, 10 volts good. So this capacitor is actually fine. So that's nice. The next one is a 100 microfarad 10 volt capacitor, and it should be open around the 100 microfarad mark, which is just down here. It's not. Oh, it's 10. Oh, I thought it was 100. Okay. That's why the thing wasn't opening. It's a 10 microfarad. Hook this back up to the tester here, and I'm gonna have to swap to a different scale because the innermost scale, which is the one I'm using, can only go down to 20. So I'm gonna have to switch this to the next lowest scale, which can go between 0.1 and 50 microfarad. So I'm going to flip this to bridge, and the 10 microfarad mark is right there, so it looks like it's already starting to open there. Let's measure a little bit higher, actually. Right there. It's measuring like 13 microfarad, so that's very close. Now we can test this one for leakage. This is a 100 volt rated cap, and I just checked that. So let's go up to 100 volts on the leakage. So 3 volts is good. 6, 10, 15, 25, 50, 100. That cap is just fine, no problems. Okay, this is the second to last cap. This is a 47 microfarad, 50 volt cap. So 47, I'm gonna flip this into the innermost scale that we're using because on this scale, 40 and 50 are very close to each other, and on the innermost scale, 40 and 50 are a lot farther away, so we can get a little more precise with it. So I'm gonna flip this to bridge, and once we flip to around the 47 microfarad mark, the eye tube should open. Right there. It's a little bit above the 50 microfarad mark, probably around 52, 53, so that's not too far off. And now we'll flip to leakage. Good at 3 volts. 6, 10, 15, 25, 50. This cap is good. And actually, you know what? It's not the second to last cap. That was the last cap. So, out of the capacitors on the power supply, all of them are good except for one. So if you look at the schematic right here for this thing's power supply, you can see that the cap right here, this 200 microfarad C6, this is the one that was leaking. So that's the one that's going to need to be replaced. And it's possible because the 69 volt fuse inside the system was blown when I first took a look at it, that this leaky cap could be a part of that. But one thing I do want to check is that if that fuse is blown, it's possible that these diodes up here or down here could be shorted. So let's check CR6, 7, 8, and 9 and see if they're shorted. So here's what I'm currently waiting for so I can plug these 3 boards into the machine and see if they work properly. The power supply, I'm waiting for a new capacitor for right here. This board is ready to go. I'm just waiting for my connector crimps to arrive so I can repin the bad connectors on these wire harnesses. On the back connectors of this board, I sanded all these down to bare copper and then put solder over them so they wouldn't rust. But I think I might have to sand down these solder connections because I think they might be a little bit too tall because I did a test fit with the harness and it was pretty tight to get on here, so I might have to sand these down a little bit so it'll fit on easier. The driver board doesn't seem like it has a problem, but I still have to wait for the connector crimps to arrive so that I can actually plug that board in. So while we wait for that, I think what we can go ahead and do is actually plug this machine in and turn it on, because I did some more looking around with the bridge rectifiers and I think they're fine. They're not open and they're not shorted, so I don't think anything catastrophic is going to happen if I plug in this machine. Now, we're going to plug this machine in without any of the boards in it, and so nothing computer controlled is going to work, but I think that the general illumination will light up because I looked at the schematic and it seems like that 6.3 volts comes right off of the transformer. So I think we can go ahead and plug this thing in and we'll see if it runs. Well, I'm going to leave you on a little bit of a cliffhanger here for the end of part 2. In the next video, we are going to power this machine on for the first time in 40 years, and then we'll go about testing everything and see what else needs to be done with this machine. We're going to kind of go through the testing phase methodically on this. We'll hook things up one at a time, and we'll just see what works and what doesn't. So look forward to part 3, and I will see you in my next video.